let's try not to.
But I don't hear. Wait. Stop.
Yes, it works. Okay, okay, are we ready? After all these technological interludes, huh? Good morning, everybody. So let's reassume where we were yesterday. I was making a kind of summary of the triumphs and limitation of the independent particle model. We have went through the calcium isotopes, which is one of the textbook examples where having the independent particle model plus the extra hypothesis that every 2 neutrons we add are coupled to 0, we can explain few things, no? The ground state spin, etc. You have probably, all of you have worked out the magnetic moments in this approximation, you get in the Smith lines, etc., etc. It is important also to compute some other properties in the independent particle model, for instance, related to electromagnetic transitions. And in this limit, you have these famous numbers that are the Weisskopf units, which represent more or less the transition strength of one transition when the degree of freedom is just one single particle. This is a reference because transitions which carry many Weisskopf units indicate the onset of collectivity. And I have put there the typical values of the electric and magnetic Weisskopf units for different multipolarities. And in the case of beta decay, the allowed and super allowed Fermi and Gamow-Teller beta decays have, in this limit, reduced transition probabilities that are order 1, corresponding to values of log ft of 3.5. Okay, let's take that as a reference. But now let's make the first unification. I was proposing to you a unified view of nuclear structure. Let's do the first step on that. And this is the idea that the independent particle model, even as simple as it is, may incorporate without any problem all the goodies of the liquid drop. So let's kill the drop, in a sense, and then we will continue. This is a summary of what we have got with the independent particle model, and this is well known, but what is less well known is that in the large A limit, the independent particle model reproduces the results of the drop. This is, have you ever done that exercise? No? No? Nobody in the hall? In the lecture room? Well, good idea. This is something original in a sense. So, let's do it. We take the independent particle model just with the harmonic oscillator. Forget about the remaining thing. The single particle energies we know. And remember that the radii of an orbit is also has a very simple expression, which is the same expression you get in the energies, but multiplied instead of h bar omega, which is the energy unit of the oscillator, by the equivalent length square, which is b squared. B squared is h bar divided by m omega. It's the same, obviously. The harmonic oscillator has a single parameter. Remember also that the degeneracy of each shell of the harmonic oscillator is p plus 1, p plus 2 for neutrons and for protons. let's now assume n equals z. Then to accommodate in these states, in this orbit, A divided by 2 identical particles, we need to fill shells up to one thing that I will call the Fermi number of the system. The principal Fermi number is the p number of the last orbit I need to fill to accommodate the number of particles. Okay? So I define this p Fermi. On the other side, experimentally, the radius of the nucleus is obtained. There I put the experiment. This is an experimental measure. We know that the radii of the nucleus varies like 1.28 to the 1/3. Then the radii of the nucleus has this expression. In the independent particle model, I can compute that, because the radius of the nucleus is just the radius of the orbits, okay? The radius of each particle from I equal 1 to A/2, and this is normalized because it's the definition. But instead of summing over the particles, I can sum over the orbits with the degeneracy p plus 1, p plus 2, and this is the value of the radius of each orbit. Okay, on the other side, to define which is the p of Fermi, I can say that I can compute that just summing the degeneracy of the orbits from 0 to pf, and this has to be A/2. So this equation gives me the value of the Fermi, this p Fermi, which is 3/2 A to the 3/2. And putting everything together now, we find, it's an exercise you will do, that a result that you find in all the textbooks, that b squared is equal to a to the power 1/3, and h bar omega is the famous 41 a to the minus 1/3. Okay, this is in the textbook. Okay, no problem. But now we can compute the total binding energy, and the total binding energy is just summing the energies. Tell me. Sorry? Sure. Huh? Because this, no, because I'm getting because the radius of the nucleus in the independent particle model is the sum of the radii of each particle divided by the number of particles. This is the definition of the radius. No, it's the definition. It's what is the radius. If you compute the radius, it's that. It's the definition of the radius, which is an average in a sense, because the radius is an average. I mean, you have a wave function, and you compute. You have to define which is the radius operator. The radius operator is 1 over a sum over a of Ri squared. That's what you are computing. And this is just 1 over a, and this is the sum over a of the radii of the orbits. This is the definition of radii. This is completely general for any system of many particles. It is irrelevant to sum from 0 to a or 0 to a divided by 2, because neutrons and protons, I have the same number of neutrons and protons. This is irrelevant. So you get this result. The total binding energy can be computed at the sum of the binding energies of every particle. That's extensive. The radius is the mean square radius is the mean square radius. The B is extensive, and at leading order, I put, when I mean leading order, is leading order in P, meaning that I have to keep the maximum power of P, and when I make a sum, I do the integral. It's like taking the limit of large P. So if I have P to the 4, the result of the sum is P to the 3. The result of the sum is P to the 4 divided by 4. It's like making an integral in the large. It's just taking limits, okay? Okay, so if I sum, I take that and I divide by A, because I'm interested in the binding energy per particle. The sum of V0 is V0A, then divided by A, and putting it here, I have V. And in the other side, I have the sum of H bar omega for all the states. Then I have to multiply again by P plus 1, P plus 2. I get a P3, which gives me the P4 divided by 4, okay? This is the leading order. I have other orders in P. I have a term in PF3, PF2, etc. But I take the approximation and take the leading order. So this, if I take the value I have gotten for PF, I get H bar omega, except I have this expression, and this gives H bar omega 8 to the power 1/3. But H bar omega goes like A to the power minus 1/3. So what I have got here is that B over A is a constant. Okay? And this is the drop. This is the volume term of the liquid drop model. So just taking this limit with the independent particle model, I have reproduced the volume term of and interpreted the volume term of the liquid drop. And this tells almost nothing. Well, it is important to get the constant value, but I get which is the reference depth of the well, which is 60 MeV, to get the value of 16, which is typically the experimental term of the mass formula. Tell me, any problem there? Yeah, no? It's okay? Okay, so this is not a lot, but let's continue. This is an exercise. You can do it, and if not, you can go to the Shalit and Fesbach book, and it is there. It is. They do that not with the harmonic oscillator, but with the Fermi gas model. But you can do it with the harmonic oscillator. It takes a couple of hours. But you go to, instead of stopping at leading order, you continue to the next order. And if you do that, you keep the terms in PF to the third, and you recover, I guarantee, the surface term of the liquid drop, now parameter free, with the right coefficient. So it is not only the volume term, it is also the surface term. Okay? So no need of anything about drops and molecules, etc. It's just the independent particle model that produces this term in a natural way. It's just taking the limit, as in the liquid drop, of large A. We are always in this thing. But what is even more interesting is that in this context, you get the symmetry term in a natural way, because the symmetry term has two origins. One is the Pauli principle, and another one is the dynamics of the neutron-proton versus neutron-neutron. Okay, next thing, and it is very easy, is that you can repeat the calculation at leading order but with n different from number of protons different to the number of neutrons. Then you write B instead, same thing, A V0, and then you have the PF of the neutrons and the PF of the protons. And you get the value of PF of the neutrons and PF of the protons, just as in the case and the previous case. Essentially, it's just instead of putting A, here you have N, and you have C, and you get this beautiful formula. Okay, but this beautiful formula gives you probably no hint about. But it is extremely easy. Another exercise, and this is really, really trivial, and I propose that you do it, is that you know that the minimum of this expression takes place for n equals c. Then do the Taylor expansion. When you do the Taylor expansion, you get the same thing we have already, which is the value of that for n equals c, obviously, and you get a term, and you develop the Taylor expansion around the minimum in n minus c. Then the linear term is absent, obviously, because we are at the minimum, and the first term goes like n minus c squared. But this is the symmetry energy. Well, then you get the symmetry energy, again parameter free, all the parameters have been fixed at 0 order, no more parameter, and you get an extra term of the form n minus c squared with a coefficient, bad luck, not bad luck, which is 16. Experimentally, it's almost double. But this is normal, because this treatment takes only the Pauli effect into account, the fact that it is better to fill the lower orbits orderly than to fill one less and another more, because you lose kinetic energy, etc. That's why the minimum is at n equals z. But there is another aspect, which is the fact that in average, the neutron-proton interaction is stronger than the proton-proton or neutron-neutron nuclear interaction. And this will contribute to this coefficient. This cannot be treated so directly. But I will propose to you something that may be even amusing. Is that you have another experimental anchor. When you, in this treatment, as you use the filling of the orbits, if you have many protons, or if you have many neutrons and less protons, the radii of the neutrons and the radii of the protons will be different. If you have more neutrons, the radius of the neutron will be larger, essentially without limit. But experimentally, this is not the case. Because of the neutron-proton interaction, radii, even if you have a neutron excess, radii tend to equalize. This is experimentally is an experimental fact due to the dynamics. But this you can incorporate in this simple model. Just instead of having the same frequency, you fix that the neutrons and protons have the same radii. Let's take, for instance, the average of the two. When you do that, in a very intelligent way, you recover the remaining part of the symmetry energy. Incorporating this extra experimental fact. Isn't it? I love that. This is really... So forget about the drop. Everything can be explained by the independent particle model. The drop is just an artifact. And well, probably if one want to go to fission and really very big things and with mechanism, well, I have nothing against the drop, really. If you need to use it, use it. Okay, which are the limits of the independent particle model? We have seen the pros, and now we go to the cons or limitation. And the pros are not bad. One thing is evident, and it is in the book. When we have protons and neutrons outside closed shells, the independent particle model fails completely. And this is mainly due to the fact that this part of the interaction that we have not incorporated in the box, in the mean field, has a term which is dominant, well beyond the painting term, which is the quadrupole interaction, which is a long-range interaction of quadrupole component. And this may favors that the nuclei become deformed. And the state of the more normal state of the nucleus is the state of being deformed, because nuclear physics is dominated by not by the spherical mean field, but by the quadrupole interaction. This is a change of paradigm, and I will insist. Okay, so and this is a case of emergency of this called more spontaneous symmetry breaking. You can in very fancy ways if you want to impress your colleagues. And this is and this is not only the limit of the independent particle model, but the limit file. I have to open another one, which is number 2. Should be here. Here we are. Okay, so in view of these limits, we have to make a different approach. But before going into that, let's navigate a little bit on the basis of the still in the naive shell model. You know that in a system of interaction fermions, the way to find the mean field is a variational procedure that consists in finding with this variational principle the optimum mean field. This is the R3-Fock approximation. If you remember the variational method, you know that if you if you vary this expression, which is the expectation value of the Hamiltonian properly normalized, what you get if you do this variational procedure is an upper bound to the exact energy. I will not. You have studied that in your courses of quantum mechanics. In the R3-Fock approximation, what you do is to write this, but limiting the values of phi to the space of the Slater determinants. If you have always a Slater determinants, you can move in this variational space, optimize. When you optimize that, which is done in a self-consistent way, in a sense you define your first Slater determinant associated to an spherical mean field, you enter in your equation, you verify that you don't satisfy the minimal, the procedure, and you turn and turn until your input and your output is the same, you are converged, and you find which is the Slater determinant which minimizes the energy. But at the same price, you get the mean field that produces this Slater determinant. This is the Artrey-Fock procedure. Okay? Okay, and this is excellent for many systems. Not so excellent for the nucleus because of this characteristic of the nuclear-nuclear interaction that I have told to you. No? Which is the problem? If you have a short distance repulsion which is huge, which is almost infinite, your particles cannot be independent. They have, because they cannot, if they try to be close, if two particles want to be close to each other enough to be in this region, they don't want to be there because the repulsion is infinite. Huh? So they cannot, and the problem is how to incorporate that in a box. And this is very difficult. That's why you cannot, with the bare interaction, you can in nuclear physics you cannot do the Artrey-Fock like in atomic physics. You have at the same time what you do is a two-step procedure that you can mix. First, you have to regularize the interaction, and then with this regularized interaction to do the Artrey-Fock procedure. And this is our problem. This is one of the basic problems in nuclear physics is still today, is how to deal. Because on one side we want to keep the interaction as neat and virgin as possible, but this interaction kills the naive independent particle model, and we need a kind of naive independent particle model as the initial basis for the treatment of the many bodies. So we are always in conflict and trying to trade off between these two extremes. This is part of the game, and it is like this. This is not textbook discussion. This is professional difficulties we face every day. At the same time, we are confident that the nucleus somehow, in some sense, it manifests as a system of independent particles. When it is not, it's probably not due really to this short-range correlation, but to medium-range correlation that are the ones we will treat in detail. So this is the question. Does the success, let's say, of the shell model guarantees proof that the nucleus move independently in a fully occupied Fermi sea, as assuming Artrey-Fock approaches? Well, there is a fact, is that the nuclear-nuclear interaction it manifests in a different way in vacuum and in a system where you have many nucleons. Because if you think kind of scattering, when you are in the nucleus, the collisions in the nuclear medium are modified by the fact that you have many states occupied. Pauli principle, in a sense, kills this part of the interaction because you cannot go to all the final states that are open to you in vacuum. And this is what is written there by Pandaripande, that the single particle motion can persist in a sense, due to the suppression of collisions by the Pauli exclusion principle. This is an excellent paper in Reviews of Modern Physics where they discuss these things that in a sense are the same kind of problems that is found in a strongly interacting Fermi systems, in any strongly interacting Fermi system like helium-3. In the problem of helium-3 you have even a stronger short-range correlation because you have an atom and things like that. Okay, there is a way out, which is the Bruckner theory or Bruckner-Hartree-Fock, which is what I told you and I summarized in a graph. Essentially, you make a transformation from this extremely repulsive nucleon interaction to something which is regularized. So you kill, you make a transformation which regularize the potential, but keeping the observables. What you want is you have an H on a correlated function, and you have an H effective and a phi effective, and you want to mirror, you want to guarantee that the observables that you get with that are the same, that the observables you get with this effective stuff. And this is Bruckner theory, more or less, this procedure of regularization in which you have to sum infinite series and things like that to get the regularized interaction. We will not deal with that, believe not. It is very important to recognize, because sometimes it is forgotten and won't be the reality of the objects that he himself has built. If you do that, and you go to an independent particle model or basis, your independent objects are not anymore neutrons and protons, are dress objects, are quasi-neutrons and quasi-protons. They are not the same. You cannot anymore use bare operators. The same transformation that you do going from here to here, you need to apply that to the observables to be consistent. And this is something that is sometimes forgotten. The price to pay is that the independent particles are now dress nucleons, and you need to use effective operators. And in spite of that, there is a persistence of the single particle stuff. This is very well shown in this beautiful experiment of electron scattering. Electron scattering is very clean. The electrons, you know well the interaction, and you explore how the charge is distributed in a nucleus. And this was an experiment made at Orsay in the electron accelerator by French collaboration in '82. And what they did was to send the electrons to two nuclei, lead-206 and thallium-205. And they got the cross section essentially for both, with many minima, etc. Very clean experiment. From this cross section, you made the Fourier transform, the anti-Fourier transform, and you get the density, the charge density that has produced that. And so they got the two densities, and they subtract the two densities. But if you do that theoretically in an independent particle model, the only difference between these two nuclei is the fact that you have a proton one in lead. You have a proton more than in thallium. And this proton in the independent particle model is in a very particular orbit, which is the 2s1/2 orbit, which you can compute with your R3 Fock and have many minima, etc. Well, this is the it's the last one. You have in lead 208, you have a magic number in proton, which is 82, okay? And the last orbit here is the 2s1/2. Thallium has a proton less. So lead has two protons here. All the rest is filled. This is lead. And 81, which is thallium, has just one proton in this orbit. This is filled. This is just one. There is no coupling because there is the s orbit, so there is no complication of couplings to the other. You have just one or two or zero, everything in these small orbits, everything. So if you write the density rho is sum over A of the wave functions square of the orbits with some normalization, okay? So in this case, you sum and you have 2 times the wave function square of the s orbit. In the other one, you have 1 time. If you subtract, you get just the square. It's a way of getting the square of a wave function in this approximation. That's why I was insisting on the beauty of the thing. And this is the experimental result. Things with error bars are the experimental data, and this line is an Artrey-Fock, Bogoliub of whatever mean field calculation made with the Egogny force, if I remember well. It doesn't matter. But you recognize it's a fingerprint that even if you have all these problems, still this shape with all the minima, etc., are present there. You don't have many cases. You need nature. Well, they did. You need to really to find the. It's a technical problem. You need to have a target which is stable and things. I think this is the best example. They tried that with. You need to have magic nuclei, and there is not so many to do that. This is probably there is nothing similar, okay? Because you cannot do that in nickel, you cannot do that in tin 132 because it is not stable. It's a serious technical problem, okay? So. But this obviously is not a theorem. This is just a case that shows the persistence of these characteristics that are associated to the independent particle model. Well, let me tell you that this has been scaled down by a factor 0.8 typically because of these correlations that make that in your independent particle description, you are considering that your nucleons are full nucleons. What tells you these experiments tell you is that these nucleons in the independent particle model, in a sense, are effective nucleons that are 0.8 the normal nucleon, or something like that, kind of effective charge or effective. At the same time, you recover the shape, but the experiment reminds you then that life is not so easy. Okay. Okay. More on the limit and a bit of relax now. More on the limits. Now you help me with the prediction of the limits of the independent particle model. This is, and we go back to double major calcium 40. These are the orbits. This is an excellent thing to have a bit of nature. This is these are the orbits around the Fermi level for calcium 40. The Fermi level will be here because all this orbit below may contain 20 protons and 20 neutrons. In the stream single shell model, this is the configuration of the ground state. We discussed just this yesterday, and we have this conclusion that the ground state of the calcium 40 was a 0+, and we were very happy. Okay. Now, we want to go a step beyond, and we want to have not only the ground state of calcium 40, but to know something about the spectrum, the excitation spectrum of calcium 40. And then we take our independent particle model, you take your independent particle model, and you tell me what to expect. I will follow your orders, and you tell me which is the spectrum that I will draw for you. You reflect, you think a little bit, and make the predictions. What I know in an energy scheme, this is energy, and I put these lines for levels. For the moment, I know that the ground state at zero energy, whatever reference energy, is a 0+. And then I want to know which are the excited state of calcium. Knowing that the experimental gap between this orbit and this orbit, the difference in energy is 7 MeV. And to help you, I will, let's say, put here, why not, 10, 20. So, tell me something about the excitation energy, spin, and parity of the first excited state of calcium-40. No? Speaker. 2+. Bravo. No. It's not a 2+. It's the prediction. I want the prediction of the model, not what is the experiment tell you. What can you do to make, what do you do to make an excited state? The ground state is filling the orbit that have the lower energy. Well, the first excited state is the one that has a bit more of energy. In this model, instead of the lowest orbit, you fill all the lowest orbit, and you take one particle and put it in the next. Do you agree? With this indication, I continue. Tell me your predictions for the excitation energy, spin, and parity of the first excited state. Well, excitation energy is simple. 7 MeV. Okay, great. 1, 0. Obviously, if you take a particle from here and you put it here, it costs you 7 MeV. Okay? So we expect things at 7 MeV, which is here. But spin and parity? Okay, 2, 0. You get 3 halves. You make a hole. And you put the particle in 7 halves. You can couple 3 halves and 7 halves. This makes several, 2, 3, 4, and 5. Okay? All of them with negative parity, because the D is positive parity and the other is negative parity. So you will expect here 2 minus, 3 minus, 4 minus, and 5 minus degenerate. And then you, instead of doing D3 half, you go to P3 half or S1 half to, well, you will have several multiplets with different combinations around, but above 7 MeV. Okay? And just to finish this thing, where do you expect the first state of positive parity? Tú ya has dicho demasiado, o sea, tú como te lo sabes. Where do you expect the first excited state with positive parity? Speak up. Probably you have the good answer. It's trivial. 14. 14? 14? Because you need to promote 2 particles to go up to recover the positive parity. So at 14, I will expect also multiplets of positive parity. This is the prediction of our independent particle model for the spectrum of calcium-40. It was here, huh? Zero plus ground state, quasi-degenerate one particle to Hall, quasi-degenerate two particle positive, etc., and so on. What is reality? This is experimental spectrum of calcium-40. Strange, isn't it? Huh? The first excited state is at 3.3 and is of positive parity. The first negative parity is at about 4, no? But there are not so many, and there is plenty of states of positive parity all around, and all in all, everything goes down. Everything is much lower in energy. But let me also tell you one thing: this organization of a state 0, 2, 4, 6, 8 make a rotational band. So it is not only that the first excited state is not negative parity, is not this two particle to Hall, is that it is a completely different version of calcium-40. It's like another object. It has nothing to do with the ground state. And here you have another of these bands here, but even more, these are transition probabilities that we'll discuss sometime. So, interesting, no? It's really a complete it's completely at variance with our prediction. We have been extremely bad. Huh? Meaning, what is the meaning? My object was to, my goal was to make clear that even in a double magic nuclei, which are like the pillars of the independent particle model, if you go beyond the ground state, you are lost. Huh? The dynamics is completely governed not by the mean field. The mean field prediction, or this prediction, is governed by the correlation. But all these things that you have not incorporated in the spherical mean field. And it is more spectacular than it seems to be, even if it is a catastrophe. If you realize that the excited 0 plus at 3 MeV is the head of a triaxial rotational band, and if you look to the structure theoretically and experimentally, it is not two particle to holes, it's 4 particle for holes. So the independent particle model would have put this 0 plus at 28 MeV. 28 MeV here. Huh? So something that at the spherical mean field level is at 28 MeV goes down 25 MeV. So it has 25 MeV of correlation energy. That's a lot. There's no other system in nature that has these characteristics. There is no other system but the nucleus that can produce this extreme limit of coherence, of collectivity, of coexistence, everything at the same time. This one, the other one at 5 MeV, is even worse, because the second 0 plus at 5 MeV is, when you analyze it, is of 8 particle, 8-hole nature. Again, now in the independent particle picture, it will have been at 56 MeV here. At the end of the day, it is at 5 MeV. It has gained 50 or so mega electron volts in correlation energy. That's the system we are trying to understand. And we realize that it is very dangerous because of this enormous correlation energy that are put here. And I will propose that from now on, we stop speaking of double magic nuclei. It is only the ground state which is double magic, not the poor nucleus. The nucleus is double magic in its ground state. And that's it. The next state, the first excited state of calcium-40 is calcium-40 deformed.
So this first excited state, which are four particles,
Yeah,
they are two neutrons, two protons.
essentially.
So can we speak already of some kind of alpha particle structure?
In the light nuclei, there will be a certain overlap with these things are many. Yeah, I know.
They are different lectures.
Yeah, but you. It is not trivial to make overlaps between a very complicated cell model configuration and an alpha clustering. But if you could do that, you will find that in light nuclei, because this same thing happens also in heavier nuclei. Calcium-40 is borderline. In the old times, this kind of comparison were made in oxygen-16, and the comparison, and there was a very substantial overlap in this many particle, many hole configuration with some kind of alpha clustering. So the answer is yes, but it is mass dependent. As you go far in mass, these overlaps are smaller. But this is true. It's a good comment because it makes a bit of a link with what you learn in the labs. So, apart from this boutade, which is not really boutade, it is just true, this brings us to the basic point, the dominance of correlations in the nuclear many-body system. So it's a system that, instead of thinking independent particle model and things, we need to realize that this system is dominated by correlation. It is not only the quadruple correlation, but also in some cases is the pairing correlation, but is the protagonist of our story are the correlations. And so what is then why have I spent so many time with the independent particle model? Because I need a basis. And I will change a little bit the point of view. And from now on, the independent particle model will not be a description of nature. Will be a very convenient basis to describe nature. This is the point. Okay? And to tell you one thing, we made this calculation. I can tell that we did this. We did the calculation to reproduce this calcium-40 some time ago. And we use an independent particle basis. But you know how many Slater determinant mixed together do you need to produce that? 100? 1,000? 1 million? 1 billion? 10 to the 9. So the basis is there. The basis is always the basis of the Slater determinant. But in order to incorporate all this correlation, you have to have 1 billion Slater determinant. I'm not joking. It's 1 billion. No? But if you have this 1 billion, you reproduce everything. In a sense, you unify the form limit with the independent particle model, and the independent particle model is your basis, simply. Okay? Okay. So once we have in our mind that the independent particle model is a basis, which has the advantage that it respects the symmetries. You could find other bases, and we'll see that later. But this is a natural basis in the sense that your box respect all the symmetries of nature. It's rotationally invariant, parity, whatever. It's perfectly physical. You have not forced anything. So, now we restart the nuclear A-body problem. Our challenge is to find the solution of a problem where we have many particles interacting with a two-body interaction, which will be something, an effective interaction, a regularized interaction. We will not use this, but this. So don't forget about that. Nowadays, we are convinced that you need, in many cases, to go beyond the level of two-body interactions, that the system, due to the complexity of the nucleons, the reduction of the degrees of freedom, in the internal degrees of freedom of the nucleons to the space of the nucleus, requires not only two-body but three-body interaction. This is natural in chiral perturbation theory and has been more or less fixed or demonstrated in light system, where you can do really solve the problem, the many body problem, almost exactly. Yes? Absolutely, absolutely. I should have put minor or whatever. This was a schematic. Obviously, there is nothing unorthodox in this. Okay. Once you solve the problem, but the problem is solved, you can go and compare with experiment. No. Okay. Let me jump that, because I will not. I don't want to interfere. So the unifying view is the interacting shell model, or you can call shell model with configuration interaction, or whatever. And this model is an approximation to the exact solution using, or the problem using effective interaction in restricted spaces. And the single particle states provide the basis in the space of occupation numbers, so-called Fock space. The many body wave functions are Slater determinants. And you can construct all the Slater, you have particles and you have a basis, and you can construct many Slater determinants, just putting the particles in different orbits. You construct a huge number of Slater determinants. And at the end, you can get, this is a complete basis in the Fock space. The number of Slater determinants in principle is infinite, but this has no sense. You can always put an energy cutoff, because at a certain limit, to have a state that are 1000 MeV of energy is physically nonsensical. Enough problems you have. But anyhow, the problem, as you will see, is very complicated in dimension. But let's go formal and make a formal solution of the problem, and then once we have the formal solution, then we will do the dirty work. But for one moment, let's be thematically pure.
Shall we stop now, or do you want to go another few
I'm free. Let me just finish this transparency and so if you have a basis of Slater determinants and you consider that your basis is complete, the exact solution can be expressed as a linear combination. Here I should have put an alpha here. This is a typo. It's a linear combination of the state of the basis. The solution of the many-body Schrödinger equation is transformed, as you know, in a secular problem. You have an infinite number of linear equations, and you have to diagonalize the matrix. So the problem of solving that is equivalent to that of getting the eigenvalues and the eigenvectors of your Hamiltonian in the basis of a Slater determinant. And this is eigenvalues and eigenvector provide the physical energies and the wave function. So formally, there is no big complication. You would say that this is simple. And a cell model calculation, interacting cell model, the dirty part is that you don't want to make infinite matrices. You can deal with very big matrices, but you have to make another step in effective interaction theory. It is to define the space of the Slater determinant that contain the relevant degrees of freedom, and then make another reduction of your interaction to this space in order to conserve all the information and pry that things work. Actually, things work, which is kind of miracle. So let's stop for a little bit. Okay, so there are techniques to compute these two-body matrix elements. In general, probably you know the Slater. In atomic physics, you use the Slater, the method of Slater, which is general. Is so general, which is generally not useful except for the Coulomb interaction. It was devised for, but for if we work in the neighborhood of the harmonic oscillator, as in nuclear physics, it's much better to use the Brody-Mosinski transformation method. That you can look everywhere, somewhere, but it is. I will not spend more time on that. Okay, so I change to the number 3. And a slide. So, and it is better to start by the beginning. Okay. Okay. So before entering in force in the many-body problem, let's understand what is the physical content of the effective nuclear interaction. It is important to realize that we should have just one effective nuclear interaction. That's is the same system. As the situation is very complicated, one can have many in the books, in the articles. You have many, but in reality, there is only one that you want to capture all the good elements of this Platonic nucleon effective interaction. So, yeah, without losing the simplicity of the Fock space, we can do a few transformations in the matrix elements to sew up the physics they contain. And for that, we follow this rule of Madeleine Dufour and Andrés Zucker, which is actually is a theorem that any effective interaction can be split in two parts, one which is called monopole and the other which is multiple. The thing is that monopole contains all the terms that are affected by an spherical Hartree-Fock variation. And it is then responsible for the global saturation and for the evolution of the spherical single particle energies. In a sense, it produces the mean field. It's the part which produces the mean field, and we know that the mean field is the drop, but not a lot more, no? Is the drop, all these things, and the basis. So this produces the basis. And another important thing is that in spherical basis, this part that we will see, if you write the operators here, which correspond to this monopole Hamiltonian, the operators here are number operators. So the monopole part of the Hamiltonian is the part of the Hamiltonian that written in the Fock space representation contains only number operators. Why is this important? Because a number operator counts the number of particles that are in orbits, but cannot change the number of particles, cannot mix. So this is the part which does not contain correlations. It's just the part related to the mean field and the evolution of the mean field without incorporating correlation. So this theorem is very important because separates the correlation part of the mean field part in a very clean way, so that you can proceed without problems. That's what I was mentioning. Huh? Okay. Now we can write the Hamiltonian in two representations. The first one is called particle-particle with these C operators. But you can make a transformation in which instead of using and writing these things like this, you can write this like this. It's just a change of ordering. Instead of starting destroying two particles and creating two particles, you make two vertices, one particle hole and particle hole. This is completely equivalent. But in this coupling, you recover things that are physically sound, because these particle hole vertices, we are used to them because they are related to transition operators, and well, have a more transparent physical meaning. But this is two things, no? Two ways of writing the thing. Huh? You have these operators are the particle-particles, and these are the particle holes. You can move from one to another using angular momentum algebra and weak algebra, and you go from the two-body matrix elements in particle-particle to two-body matrix elements in particle-hole, or vice versa, with a transformation which is called a Rakach transformation. As you see, there is nothing there except a 6J symbol here. Huh? You decouple, recouple, sum, and at the end of all the Klebs-Gordon coefficients make up this Rakach coefficient. Bien. The operators, this is important. The operators S, R, R, gamma equal to 0. Gamma is a spin, isospin. These are the number operators. So if you write, and that you know, obviously, you write A, dagger, orbit A, and you couple to 0 a spin and isospin, this is the number operator for the orbit A. Okay? No problem, simple, transparent. This means that I will write the monopole Hamiltonian in general. In general, you can couple R and R prime with the same quantum numbers, and only differences in the radial quantum numbers to 0. And these are the spherical particle hole vertices, and this should be 0 if the monopole Hamiltonian satisfies Hartree-Fock self-consistency. And we assume that we are in a basis that our Fock space basis satisfies this Hartree-Fock self-consistency. So the monopole Hamiltonian can be written like that. You will have number operators with some coefficients. You sum over neutrons and protons and orbits of neutrons and protons, and then you have these are the linear operators, but you have also quadratic operators in the numbers. You sum over all the orbits and over protons and neutrons, and these coefficients are the averages of the two-body matrix elements. And this is normal, because if you are spherical and if you get the monopole, there is no sense, no reason to have any dependence on the coupling. So you average all the couplings, spatial couplings, and these are the coefficients that go with the number operators. These coefficients are called, you can name it centroids of the interaction or averages of the two-body matrix elements. So this is a very special part of the interaction that make the coefficients of the number operators. And you can verify that the expectation value of the full Hamiltonian in a Slater determinant for closed shell, which is the energy in the Hartree-Fock approximation, which has this expression, if you write it in the coupled formalism, is, you can write it like this, but essentially, if you sum over JT all these things, you have the centroids. So the Hartree-Fock, the only thing that contributes to the Hartree-Fock energy is the monopole Hamiltonian. So, I mean, monopole Hamiltonian and Hartree-Fock energies are the same. This is just to verify that we are speaking. And another important thing is that the evolution of the spherical single particle energies with the number of particles in a valence space is just dictated by the monopole. That's to say that if you start imagine that you have several orbits, I, J, etc., in your valence space at order 0. This means that they are separated by energies. You have epsilon 1, epsilon 2, etc., etc. This is this. And correspond to a background in which there are particles in some other orbits, if you want, or even in these orbits, correspond to an initial condition with a background. And then you change the number of particles, you put particles in orbits, and it is evident that if you compute the epsilons in this new situation, in which you have another distribution of particles, this orbit can have moved here, this here, etc. You can find the different values of these effective single particle energies when you change your initial conditions, if you want. And this is just this incorporates only the monopole Hamiltonian. Don't enter into the details of configuration dependent, etc. But we will see that this is very important. Because when we connect the remaining part of the Hamiltonian, having configurations, essentially, different configuration, close or far apart, is crucial. Essentially, because if you have things that are very close to each other, they will mix easily. While if they are far apart, even if their interaction is large, the mixing will be killed. So this is very important, and our understanding of the physics will be like a two-step again system. The monopole field will produce the energies, the starting energies of the many body configurations, and the rest, the correlators, will mix this configuration as they can, no? In a sense. Or if you want, the monopole field will contribute in this big matrix to the diagonal matrix elements, mainly, and then the others will mix the things. But if you split apart enormously the configuration, then it is more difficult to get mixing, then it is more difficult to get coherence, then it is impossible to get collective emergence behavior. So both elements of the Hamiltonian play with each other to produce the physics at the end of the day. Okay. Important part of the multiple Hamiltonian. For instance, this state, this operator coupled to gamma equals 0, creates a pair of particles coupled to J equals 0. So these terms of the Hamiltonian are the pairing Hamiltonians. So it is clear. This is the pairing Hamiltonian. We have there localized clearly the pairing Hamiltonian. You create a pair of particles coupled to J equals 0, and you kill a pair of particles, and you count the number of pairs, because this is counting pairs, no? And you add, each time that you count a pair, you put in your basket the value of the matrix element, which is the energy you gain making the pair. Is it clear with this market image? No? Other operators that we can give a physical meaning are, in the other representation, S gamma are typical vertices of multipolarity gamma. For instance, if gamma is equal to J equal 1, L equals 0, T equal 1, you have an interaction which is a spin-isospin interaction. But this is a part of the interaction we knew from the deuteron, etc. This is the Gamow-Teller channel of the interaction. And the most important term, apart from this, is S when gamma is equal to 2, J equal 2, T equals 0, R of quadruple type is R squared Y2. And they are the ones that are responsible, these terms, for the existence of the form nuclei. If you put with quadruple shape, if you make here gamma equal 3 and negative parity, this will be the octuple interaction that makes nuclei which are pear shaped. They are less frequent, but some decide to do that. And if you analyze all the effective nuclear-nuclear interactions that are in the markets, you discover that the multiple Hamiltonian is universal and is dominated by isovector and isoscalar pairing, quadruple, octuple of very simple nature. So, analyzing the interaction, we discover the simplicity of the interaction. We have pairing plus quadruple plus octuple of relatively simple nature. This is not to say that you can reduce the interaction to these things. You better use everything you have. But if you have this analysis, you can understand what will be the physics output before doing the calculation. And this is very important. You can really know the physics, even if at the you want to compare at the end with experimental numbers, you use the full artillery, all the things. But in order to understand what is going on, is excellent to understand the interaction. Couple of comments. We have a problem. This is a problem which has been with us for many, many years, which setting in this context is the following. When you compute from first principle the effective interaction, the multiple part is always good. But the monopole part varies widely and in general is bad all the time. This has been a problem for many, many years. It was connected to other basic problems. For instance, this effective interaction have difficulties to reproduce the properties of saturation of the nucleus to get at the same time the right size and the right density. And this has been a standing problem for years and years. And maybe now we are solving it. And solving both problems that are related essentially to the monopole Hamiltonian demands probably the use of free body forces. But this is work going on, work in progress at the limit of our research. This is really something which is not finished, and many people is working in these things. Huh? But I wanted just to mention that. So, let's put the heuristics of the effective interaction and how we proceed. We take the effective interaction, we extract the monopole, we extract the isovector and isoscalar, we change to the particle Hall representation, and even if in the actual calculation we must use the full interaction, we can write a schematic version of the interaction. It contains the monopole, these two pairing channels, and the multiple channels. And the heuristic will be what I will do in this course, because what I will do is to solve problems just taking one or two of these pieces, because in general, if you take one or two of these pieces, you can have an analytic solution and a very clean solution, which is not numerical. And we will, in the lectures, we will take first, I think I have started with that, we will solve a case where we take monopole, very simple monopole, plus pairing, and solve the pairing problem in one shell, in several shells, etc., etc. And this, we will explain the superfluidity in nuclear physics, which is due only to this part. Then we will forget about that, take a monopole plus a quadrupole, and explain another coherent mode, which are the nuclear vibrations, the nuclear phonons. We will build the nuclear phonons associated to the vibrational excitation of the nucleus, okay? And this will be another example. But then sometimes this interaction is strong enough to move from vibrations to rotations, just to make the nucleus will prefer to break the symmetry to become elongated or flat, and then rotate. This is the most frequent situation in nuclear physics. This is an example of spontaneous symmetry breaking, and we will treat it also in a very simple limit, using that. In reality, professionally, I will say, you don't do that. You put everything together, but it is important to know which are the limits that one may expect. And it is important also to realize that the interaction is unique. We consider that the interaction is unique. So the different behavior of the different nuclei, which is very rapid, you move 2 units of neutrons and protons, and you get a nucleus which is deformed or not deformed or dominated, so the change is very rapid. Well, as the interaction is single interaction, so the manifestations of this interaction, this universal interaction, depend on the structure of the mean field around the Fermi level. Depending on how these orbits are in a given nuclei, how have they evolved, you will produce with the same interaction different physical manifestations. This is the point. For instance, examples that you can imagine trivial. If the spherical mean field around the Fermi surface have such orbits that make the pairing interaction dominant, completely dominant, and if the mean field is, the orbits are degenerate enough, you produce a superfluid. That's it. We'll see that. You produce nuclear superfluidity. But if the quadrupole interaction is dominant, the nucleus will acquire permanent deformation. But imagine you make all your orbits degenerate. All the monopole you put to 0. So all your orbits, all your configurations have the same starting energy, which is 0. So they are all degenerates. So the mix is maximal, absolutely maximal. And there will be the quadrupole becoming crazy, completely, well, happy and crazy, and making, instead of nuclei, they will make needles of nuclear matter that will be, by the way, superfluid. Funny. And there is this marginal role that now play the magic nuclei that are more the exception that we thought. Magic nuclei are spherical despite the strong multipole interaction because the large gaps in the spherical mean field protect them. But if you think a little bit about the protection of the mean field, it was a quite weak protection. Calcium 40, which is one of our cases of double magic nuclei, has this form of 3 MeV coming from the clouds. So really it is double magic by in a sense. These states have moved a lot and just have remained on this. Many other cases in wisdom told us that we should some kind of magicity where reality has told us that this magicity has disappeared because in other cases this down-sloping deformed configuration don't stop at 3 MeV, just cross the ground state, the spherical ground state and become let's say the strong, and how do you say that, the spherical configuration that they eliminate the spherical configurations and becoming the ground state themselves. So this is the setting of the stage. So now, as I promised you, I will visit the 3 kind of collectivities of coherence present in nuclear physics and explain it in simple models. That's the goal of the next lectures. And but I will start with a very simple model. So simple that I have 2 Slater determinants. And these 2 Slater determinants, the ampere term, let's say, before mixing, I can compute the energy of both the Slater determinant, one I put to 0 and another to delta. And the 2 Slater determinants are connected by the multiple Hamiltonian by an off-diagonal matrix element, a small delta. In the limit in which delta is much smaller than the separation, I can use perturbation theory, and I will have now essentially little fun. No? I will have one state with a little mix of the other in perturbation theory and the other. But let's go to the limit in which this is 0. They are degenerate, or equivalently delta is very small compared with a small delta. Then the result, which is you can solve because it's a 2 by 2 matrix, is obviously that the two states are mixed 50-50. And one of this mixing will gain an energy which will be delta. If you put 0, 0, the eigenvalues are delta, plus delta, and minus delta to conserve the trace. And so there is one state, which is this mixing of two, which gains energy, the maximum energy that you have in the system, and the other lose the energy, is the coherent and the anti-coherent. Well, this simple example contains the idea that we will have. In a sense, delta depends in a more complicated problem. Delta depends on the multiple Hamiltonian, but also in the matching of the configurations that I will mix. So that's why the structure of the spherical mean field around the Fermi surface is completely dominant. It is not only the degree, it is fundamental in two aspects. One, because of the diagonal. If the configuration are close to each other, this makes the mixing simpler. But also, there should be configuration that have large off-diagonal matrix element with a multiple Hamiltonian, because even if this separation in the diagonal is small, if this is very small, nothing happens. So to get coherence, both things are necessary, that the configuration are not very far apart, and that the matrix element that connect the configuration are strong enough. Okay? I promise with this, because I prefer to finish with a more serious thing. Let's generalize this example. This is a degenerate case with n Slater determinant with equal and attractive diagonal matrix elements and off-diagonal ones of the same magnitude. So the problem is to diagonalize this funny matrix, which has only ones. This funny matrix, as you can realize, has all the eigenvalues, is extremely singular. Determinant is 0, 0. You reduce at continuous mean 0. So the range of the matrix is 1. E and the eigenvalues are all 0, but the trace has to be conserved. So if all the eigenvalues are 0, you need to have 1, which is exactly the dimension of this G here multiplied by the dimension of the matrix. So this is a extreme case of coherence in a mathematical model, because it's obvious. You realize what happened before mixing. You take the diagonal, and you had many states that have an energy which is 1. In some unit, this is 1. You connect the mixing, and then all the states except 1 are here, and 1 has minus n as energy. Okay? To compensate for the others. And this state, which is the coherent state, if you compute the eigen vector, is the mixing of the n unperturbed states with all the same amplitudes. It's very democratic. All the states have an amplitude which is 1 over square root of n. This is a beautiful example. It's maximum coherence. And all the things that we are And this is the basis, if you want, the mathematical basis of the physics that we'll be describing tomorrow. And now let's go for lunch. Okay?